Perfect. Okay, I think we are ready to start. So I just want to introduce the two speakers. So we have Ayah Hamdan. Ayah Hamdan presented before, and so she's a master in public health student at Harvard School of Public Health. She's Palestinian American, and she has interest in global health and kind of teaching medical students and other students in low to middle income countries. Zahra Al-Khateeb, she's a graduate from Harvard School of Public Health and master in economics, and she's working in different companies, including Hikma and Vertex, as a senior economist. And my apologies if I misspelled any of the bios you've sent to me. So we'll have Zahra. I think Zahra, are you sharing your screen? And do you want to start the presentation?
Can everyone see our screen? Just type in the message if you can't see anything. Actually, how do I see that?
The chats are showing up in the, yep.
Oh.
Yes.
Okay, awesome.
Great.
Perfect.
Okay, then we will begin. So hi, everybody. If you were here for the last presentation, it's very good to see you again. I'm very excited to be here and be with OxPal. And at any point, if there are any issues with the audio or the visuals, or if you have any questions at all, feel free to interrupt. You can unmute yourself or type in the chat. And Usaid will also be here to help moderate the presentation. So Zahra and I will be speaking to you all about a very brief overview to hypothesis testing and univariate analysis in biostatistics. So here's the agenda of what we'll be discussing. So throughout the presentation, just keep in mind that this is meant to be a very, very brief introduction. I think maybe some of you might have more experience with biostatistics than others, but I understand that most of you have very limited, very minimal experience. So we don't want to go into too much detail. We're trying to keep it very brief. At some points we share equations and things like that, but this is just intended to kind of spark your interest in biostatistics research and to encourage you all to pursue it further and look into it more. So we'll start with data types, measures of central tendency and dispersion, and those two will be very brief because I think you got an overview to those in a previous lecture. And then we'll spend the majority of the lecture talking about hypothesis testing, p-values, confidence intervals, parametric and non-parametric tests. Okay, so SPSS Software, I think Usaid mentioned that you all were able to download it. It's free now because of Corona. If you need the link to download, it was shared in the OxPal Facebook, LinkedIn posts, and Usaid can send the link again if anyone needs it. But SPSS is a software that we use to calculate a lot of these measures and do data analysis. In public health research, it's used more internationally than in the United States. But we'll be sharing screenshots of SPSS throughout the lecture so that you can see how this is applicable to using software. So you've all learned this before, the different types of data, continuous, binary or dichotomous, nominal categorical, ordinal, count outcomes. So we'll be using different types of data throughout the presentation, but you've all seen this before, so I won't talk about it too much, but of course, if you have any questions, let me know. And descriptive statistics, so are usually categorized by measures of central tendency and measures of dispersion. Measures of central tendency, the main ones are mean, median, mode, Mean is mostly sensitive to outliers. So in that case, we would use median. Mode is not used very frequently, but it's which number or value occurs most frequently in the data set. And then you have measures of dispersion. Is another important way of describing the data. So the main ones used are range, interquartile range, and standard deviation. Range and IQR are similar. Range is just the maximum minus the minimum. IQR is the third quartile minus the first quartile. And standard deviation, we will touch upon more, but I think this is a review for you all. Variance is another very important measure of dispersion. So variance is just the standard deviation squared. If the variance is equal to 0, then that implies that all of the data points are identical. These two are the equations for population variance and sample variance. So they're very similar, but we use the sample variance when we're talking specifically to our study population, and then hopefully make inferences about the entire population. So that's the equation, but you usually won't be needing the equation, especially if you're using software like SPSS. And variance will be coming up once you start to learn the different types of hypothesis tests that you can do. So before we get into the most important parts of the lecture, just to make sure that we're all on the same page. So feel free to type in the chat, feel free to unmute yourself if you want to speak. The first review question, which measure of central tendency is most sensitive to outliers? Is it mean, median, or mode? So type in the chat or unmute yourself. Mean, is that Asmat? Okay, Asmat says mean. Everyone
yeah, it
agrees?
says mean. Dua says mean.
Okay, great. You guys are correct. Well done. And the main differences between range and interquartile range.
Yep, Ahmed says max minus min is range.
Yep, range is maximum value minus the minimum value.
Anyone want to tell us what IQR is?
Ahmed, IQR is the third minus the first quartile, yeah. So they're similar, they're both measures of dispersion. Thank you, Ahmed. And then the third question, what are the main differences between standard deviation and variance? Ahmed is the most awake, the most active. So yes, the variance is the standard deviation squared. And we use variance a lot when we decide which hypothesis tests that we want to use. Okay, thank you all so much. So we can move on to inferential statistics. So what we've talked about so far, descriptive statistics are used to describe the different data sets, to organize, to summarize, and just a way of presenting what kind of data that you have and that you're working with. And then once you start to conduct research studies, you'll have to focus a lot on inferential statistics. So inferential statistics are used to make inferences from your sample size to the general population. And that's what we focus on with hypothesis testing, and to try and make predictions about the future specific to our study.
Okay, great. So before we get into the mechanics of hypothesis testing, and Ayah and I will both go into a couple different concrete examples of different tests. There are a lot of different statistical tests, and it can be a little bit overwhelming to kind of see that list, and each one has its own calculations, etc. I think just taking it back to the general concept of what a hypothesis test is just important, especially in the medical field in terms of how you're going about designing a study or interpreting data. So just really quickly, would love to just hear from the group in terms of what do you think of when you hear the word hypothesis? Because that's a word that we use a lot in science, and it's very specific to biostatistics in a little bit of a different way. But would just love to, if you guys can just type in the chat, what comes to mind when you hear the word hypothesis? Okay, Asma says a research question to be tested. Awesome. An assumption, yep. Get one more. A statement that might be right. I love that. Great. Those are all great answers, all correct. Basically, we think of a hypothesis as an educated guess about whatever we're seeing in the world around you. I think to figure out a relationship, exactly. And so I think the core underlying sort of feature of a hypothesis, specifically as it relates to statistics also, is that it needs to be testable, either through your experiments or the test that you're running. It needs to be able to be what we call pressure tested. So if you're in the medical field and you think you're giving a new medicine to a patient, will it work? That's a hypothesis. A hypothesis might be that, yes, it will work. And so hypothesis testing, specifically in statistics, is our methods that we use to test the results of experiments to see if the results are actually meaningful. And so we're trying to detect, so say if we have results that are comparing two groups, like two patient groups, for example, the main question that we're asking is, why is there a difference between, you might get a mean or a median value between two groups on a certain metric. And what we're asking is, why are there differences between what we're observing about those two groups? Is it due to an actual effect? Is it due to bias or confounding factors? Specifically for hypothesis testing and statistics, what we're actually trying to design our tests around is to ask if the difference that we're observing between the two groups is actually due to what we call random chance. And so a little bit more about kind of how this is kind of a review of the last slide actually, but really when we think about hypothesis testing, there are really just two options. We either accept a hypothesis that we state or formulate after we collect the data and test it, or we reject that hypothesis. So everything rests on that original hypothesis statement that you're going to make. And again, what we're trying to do here is to detect if the difference between two groups is significant and did or did not occur by random chance. And so going back to the statements, right, that we're talking about. So in hypothesis testing and statistics, the main thing to keep in mind is what we call the null hypothesis. And that is the basis of every statistical test. And that null hypothesis is basically a statement saying that we believe that the difference between two groups is caused by random chance, and there is no what we call significant difference between the two means or the two medians of two certain groups. Then obviously on the alternative side, we have the alternate hypothesis, which suggests that the difference is actually real, and that's in direct contradiction with the null hypothesis. And so obviously only one of those can be true. And so that's what you're running your statistical test, and that's what the different metrics and parameters that we'll get into, that's what they're going to end up telling you. So an example that might be more relatable for you guys as a null hypothesis is to say we said the mean tumor size between a group of relapsing lung patients is the same as the mean tumor size in progressive lung cancer patients. So we might actually be looking at a set of data in which the mean tumor size between the two groups is different, but we don't know if the difference is meaningful enough to say that actually, no, there is a actual difference between the two groups. And that's what we are testing. So conventionally, we try to break hypothesis testing down into 5 basic steps. One is that we make our assumptions. Each kind of type of statistical test has specific assumptions around the data that you're working with. So we try to categorize those assumptions and make sure that if we're going to apply a statistical test, that our actual data and the way it looks meets those requirements. Then we have a very specific, very clear null hypothesis statement. So I just brought it back from the last slide that we're hypothesizing. Again, it's the null hypothesis. So the null hypothesis is saying we believe that the mean tumor size between these 2 patient groups is the same. Oops, I think the numbers here are wrong. But so number 3, the third step would be that we select what's called the sampling distribution. And I'll go over that in a little bit, and establish what we think is the critical region or the threshold by which we're going to determine if the results are significant or not. Then what we do is actually run the test. We compute the test statistic, which are different for different tests, and then a confidence interval and a p-value. All of things that we'll go into on the next few slides. And then obviously, importantly, we then interpret the results and then make a decision on whether we are going to accept or reject that null hypothesis. Okay, so I'm sure some of you have heard of p-values before, but I think it is important to review because they can often be very misinterpreted, as well as, you know, z-scores and confidence intervals. So I think it's good to just have a refresher, even if you've seen this before, just to understand. The p-value actually is something that is in debate quite a bit more recently in the statistical literature. So, but it is still kind of the gold standard of what we use in statistics in public health to determine if results are significant or if an effect is significant. So really what the p-value is the probability that your observations or something even more extreme to those observations still correlates or holds true under that null hypothesis. So kind of accordingly, if your p-value is small, the smaller the p-value is, the more confidence you can have that you can actually reject the null hypothesis and conclude that the difference that you're observing between your 2 groups is not just due to chance and is what we call, that you've probably been reading a lot in any papers that you read, is what we use the phrase statistically significant. And so you can see on this table in the bottom right, generally in the literature, we conventionally go towards any p-value that your statistical test spits out that is less than 0.05 or less than 5%. That's what we conventionally use as an acceptable threshold for calling results statistically significant. But that being said, I think depending on the journal or depending on the rigor of research that you're trying to conduct, 0.1% is actually used a lot more often. So we won't go into the mechanics of this formula, honestly. The SPSS will calculate all of this for you, but just to kind of show you how these things are related. But in order to calculate the actual p-value, you're calculating what's called a t-statistic, and you'll see that in some of the other tests that we go into. But the p-value is directly related to the spread or the variance of the sample, as well as obviously the sample size, etc. And don't worry about this formula. It looks a lot more complicated than it is. Okay. So now we're going to jump into z-scores and confidence intervals. These are also extremely important when we're thinking about how to generalize from what we observe about a certain sample to a larger population. So a z-score is actually really useful. So it helps us understand how much bigger or smaller an observation that we see is related to the population mean. And the z-score is specifically expressed in units of standard deviation. So if you look at the graph with the green and the blue, so if we have a regular normal distribution, which hopefully you guys are familiar with, just like a classic bell curve, if you have a normal distribution, that's going to be taking from your actual data. So you can have whatever numbers in there. So I've just put any numbers in here. And then when we try to calculate z-scores, what the math is actually doing is standardizing your normal distribution to make it interpretable in units of standard deviation, so +1, +2, +3 standard deviations away from the true population mean. So we're able to standardize those raw scores and convert them to z-scores. And that allows us to actually calculate the probability of a certain observation happening within the standard normal distribution, and allows us to compare scores between two different groups.
Skip the CI.
It's next. I switched them. And so the z-score is actually a pretty simple formula, but it's really just your observed score or observed value minus the population mean divided by the standard deviation. And now going to the confidence interval. So a confidence interval is really just a set of values that we believe the true population mean falls within based on the sample that we've drawn. So we're taking a certain sample and then we run a test, and then a confidence interval comes back and we get a certain value for the mean that we believe is related to the population mean. Then the confidence interval tells us that we believe that the true population mean falls within X and Y. And it's obviously going to be affected by both your variance and your sample size. And that it gives you a range around the estimate that you're getting that allows you to have, a 95% confidence or a 99% confidence that your actual population mean is covered within that interval. So if you look on the top here, I've just put two examples, but if you have a confidence interval of 4.1 to 4.5 around an observation that's 4.4 versus a 3.2 to 8.6, that's a much larger confidence interval. So we in research, we prefer to see very, very tight confidence intervals. That shows you that there's less room for error in your experiment. Okay. So the confidence interval and the p-value kind of together, and you'll see this when we get to the results, because it's kind of hard to interpret obviously here without going through an example, but the confidence interval and the p-value together are really what help kind of paint the picture of how reliable your results are, how meaningful they are. If you have a tight confidence interval and a very, very small p-value, you can basically feel good or feel confident enough, depending on what the numbers are, that you're seeing an actual effect in your experiment. Okay, so now before we jump to examples of specific statistical tests and run through some of the SPSS screenshots as well and try to help you understand how to interpret some of these things, we wanted to just take a little bit of a step back and describe the two main types of tests that we use in hypothesis testing, and these are parametric tests versus non-parametric tests. So parametric tests, the word parameter, you guys might be familiar with, but the reason why it's called a parametric test is that it's basically uses the assumption that a certain set of data can be measured with parameters. And so that's why parametric tests, we generally use them when our data can be described with a normal distribution, or maybe it is a skewed or non-normal distribution, but the mean is representative of the entire population or entire kind of individual samples. It's also really useful when the spread between two groups is actually different, or if you need more statistical power to detect an effect. So better for larger sample sizes. And then, so Ayah's going to talk through a couple of those parametric tests in the next few slides. And then for non-parametric tests, these are much more used when you have a very small sample size, or if your population, or if your question, or if your sample is better represented by the median. And those usually go hand in hand. Also, if you have ordinal data or data that's in ranks, or if you have very large outliers that you can't get rid of in your data set, it's better to use parametric tests. And these are all examples here of the mainly used non-parametric and parametric tests, and we'll be going through a couple of these today. Okay, so I know that was a lot thrown at you. These are really just, again, high-level concepts that are all used and calculated by SPSS or any statistical software for you, and it's just to help this is kind of just to help you understand and get a quick intro to how do we think about, are the results of our hypothesis test significant or not? So just really quickly as a review, if you can just type in the chat, what does hypothesis testing try to measure regarding the difference between two groups? Okay, I see some people put actual effect, and some people are putting chance. So yeah, I can see how that can be a little confusing. I definitely want to reiterate that what hypothesis testing and statistics is doing, and what the p-value is trying to do, is try to understand how probable is it that the actual difference between two groups that you're observing is due to chance or not. So the p-value is, oh, sorry. Yeah, I can say that again. So what we're doing in hypothesis testing is trying to measure how likely is it that the difference between the two groups that you're observing is due to random chance, as opposed to, that's what the null hypothesis is doing. It's saying that this was not due. Does that make sense? So it would be chance. Okay. Okay. All right. Second question. Can someone tell me what would you do if you ran a statistical test and you got a p-value of less than 0.05, and say you were evaluating the mean pain scores at 24 weeks post-treatment of a cohort of cancer patients, and you say you had cohort of cancer patients from Nablus and cohort of cancer patients from Gaza, and you were looking at their average pain scores at 24 weeks after treatment, and you ran your statistical test and you got a p-value of less than 0.05. What would your conclusion be? If it's easier, perfect, yeah. Thank you, Ibrahim. Yes, so if you see a p-value less than 0.05, exactly, Allah, that's perfect. Yeah, you said it really well. So the chance that, so if you got a p-value of less than 0.05, that would be telling you that the probability that the result is due to chance alone is less than 5%. So that would allow us to reject the null hypothesis that the two means are the same. Exactly, thank you. That's perfect. Okay, and then thirdly, what does a z-score allow you to do? So a z-score definitely tells you how far the data is from the mean, but what is unique about it? What does it do to your distribution? Okay, so these are all correct. I would say probably what's the most important thing to remember about the z-score is that it tells you how far you are from the mean in units of standard deviation, so that you can compare between groups, so that it's standardizing the normal distribution. So I think that's the coolest part about the z-score. Okay, I think we can jump.
Okay, great. Again, إذا في أي أسئلة please type in the chat. برضو راح نعمل وقت Q&A بعد lecture. So yeah, please don't hesitate to ask questions. Zahra and I are happy to pause at any point. But just moving forward, so when you are choosing a statistical technique, you start with the research question hypothesis, and then you have to consider how many variables that you have in your question. So this lecture is only focused on univariate analysis. Uni meaning one, of one variable, but there's also bivariate analysis with 2 variables and multivariate analysis with multiple variables. So we're focusing only on the first column here, univariate analysis. And z-test is the most basic parametric test that we have in biostatistics. So it's testing the significance of differences between 2 means of samples. So when you run a z-test looking at a z-distribution, it is normally distributed. You have a mean of 0 and a standard deviation equal to 1. With the z-test, the population variance is known. So the assumptions when you run this type of test is that the population is approximately normal or that you have a very large sample. So in order to run a z-test, you have to have a sample size that is larger than 30. The data must be quantitative as opposed to qualitative, and the variable is assumed to follow a normal distribution in the general population. So alternatively, we have a t-test used to study the mean of populations. So you use t-test when the sample size is small, below 30, whereas z-test, the sample size is greater than 30. When you run a t-test, the test statistic is known as t, the t statistic, and the curve of the distribution is flatter than it is with the z distribution. So they're usually both bell curved, but it's just a flatter curve. And with the t-test, you usually do not know what the population variance is. But an important concept is that t approaches z as n, the sample size increases. So if you have a very large n, then t starts to look like z in terms of what the distribution is like. So that's why I provided this graph here. I think it's very clear. It explains the relationship very well. So you see the blue curve is a z distribution. That's the standard normal, mean 0, standard deviation 1. T distribution that is close to 30. It looks very similar to the blue curve. And if the sample size is significantly smaller than 30, then the t distribution is more of a flat curve. But as the sample size increases, they'll look a lot more similar in distribution. So very quick review. Here's an example study, just a simple example study. A random sample of 26 graduates scored 458 on the sociology test, standard deviation of 20. Is this significantly different from the population average? And the mu is equal to 440. So looking at this type of very general study, would you conduct a t-test or a z-test? T-test. And does anybody want to tell us why? Ibrahim, because n is less than 30. Yes, okay, wonderful. I'm glad you're all paying attention. So this should be easy, really similar question. In a recent survey, 55% of the population were found to be aware of modes of HIV transmission. A random sample of 150 urban persons showed that 49% of them were aware of the same. Is the difference significant? So this is an example of what kind of test. Okay, Z because more than 30. Perfect, okay, so you all understand that. We can move on. So yeah, Z test because the sample size is greater than 30. So another type of common test that we use is the chi-square test. You use chi-square when you have categorical data and when you want to determine if the observed frequencies differ from the expected. So this is very similar to what Zahra introduced us to. Is the association that we observe real or was it by chance? But this is focusing on categorical data and looking at observed versus expected. So this is the equation for chi-squared statistic for those who are curious. But again, this is something that SPSS, R, Stata, SAS, different types of programming softwares will always compute for you. And an example that I thought could help frame how you run a chi-square test, or an example in which you would run a chi-square test, is if you're looking at an exposure of education level, high school, college, master's, doctorate, PhD, to the outcome of marital status. So is there an association between your education level and whether you're married or not, basically? So in this case, the null hypothesis would be that there is a significant, oh, I think I had it switched. Yeah. Oh, I'm so sorry. I had it switched by accident. So swap it. For the null hypothesis, no significant association between education level and marital status. And the alternative hypothesis is that there is a significant association between education level and marital status. So sorry about the typo, but just flip them. And this is what the chi-squared test looks like in SPSS. So you use a command called Crosstabs, and that allows you to get your chi-squared statistics. So that would be what's in the value column. Degrees of freedom with chi-square tests are 1. And then it says the significance level, otherwise known as the p-value. So the value here in the red circle is 0.035, and that is the p-value for your Pearson chi-square test. So looking at the example that I just mentioned, marital status being affected by education level, what conclusion would we come to with a p-value of 0.035? Again, sorry, keeping in mind that the null and alternative are switched. So the null is that there is no significant association between education and marriage, and the alternative is that there is a significant association between education and marriage. So using a p-value of 0.035, would you reject the null here or accept it? And what would be the conclusion? The results are significant. Yep. Yeah, so you would reject the null hypothesis because the p-value is below 0.05. And since you reject the null hypothesis, you would conclude that there is indeed a significant association between education level and marital status. So you would reject the null and support the alternative hypothesis. Great, good job, everybody. So moving on to another important test is the ANOVA test. So we use t-test when we're comparing 2 group means. ANOVA is when you're comparing more than 2, so 3 or more different types of groups. So you're testing for a difference between means, and instead of the t statistic or the chi-squared statistic, in this case it would be the f statistic. And this is an example of what the output looks like in SPSS. You have the ANOVA test, one-way ANOVA, and your significance level, otherwise it's known as your p-value, is 0.018. And so I put this up hopefully just to kind of make you laugh more than anything. So this is an example of a test flow chart that one of my professors shared with me at the beginning of my degree. And these are the many different types of statistical tests that you can do depending on the type of data that you're looking at. So as you can see, there are many, many different types of tests that you can use to determine associations. and I cut the flowchart in half, and we have focused so far on just 4 different types of statistical tests, but there are many, many more. So Zahra is going to continue to talk about different types of tests that we can run.
Yeah, so I'm gonna do a quick run through of an example of a non-parametric test. So if you remember, non-parametric tests are generally used when you have a non-normal distribution and you have a very small sample size. I'm gonna try to walk you through what the SPSS steps would be as well, to try to see if that can resonate with you guys a little more than some of our other stuff. But so generally, the Wilcoxon signed rank test, it's a very common test that's used to try to determine whether you have, whether one of your samples, if you have 2 independent samples, if one of them is generally larger than the other. So you're asking, the core question that you're asking is the median of the 2 samples equal? That's your null hypothesis. So here you can see on the left, the null hypothesis is that distribution A looks exactly like distribution B, so the median would be equal. And the alternative hypothesis would be that, say, distribution of sample A is greater than distribution B. So that's what we're doing. This is a very specific question, and that's when you would use the Wilcoxon signed rank test. And going back to Ayah's flowcharts, because there's so many tests there, each of them is best for a very specific question. So when you actually get into choosing your hypothesis, what type of test you're doing, that's when it gets to be really important to understand the detailed mechanics of when to use what. And this is an example of just a very specific case. Okay, so I'm gonna try to put this in context of a question you might actually get, in your own research or in your own field. So say you had a study, say you're a researcher, a pain physician, and you're interested in finding ways to reduce lower back pain in people without having to use medicine. And say you think that maybe having acupuncture, if the patient has acupuncture in the lower back, that maybe it helps them reduce their back pain. So say you recruit 25 participants to your study. And at the beginning of your study, you ask each patient to rate their back pain on a scale of 1 to 10. And say 10 means greatest level of pain, 1 means lowest. And then, so that's at the beginning, at baseline. And then say every week, the patient comes and records their level of pain. And then after 4 weeks, they're asked, every week they come in twice to get acupuncture. And then after 4 weeks, they come in again to your clinic and you ask them again, what is your level of back pain on a scale of 1 to 10? And so you have 2 scores for each patient. You have the baseline and then you have after 4 weeks. And so your research question is, did the levels of back pain that people are seeing after the acupuncture, are those actually significantly different or not? And so this is an example of when we would run a Wilcoxon signed rank test. So before I go into that, just going back to the prior slide, just to see if everyone sort of caught on, but why would this specific problem be appropriate for a Wilcoxon signed rank test or a non-parametric test? Yeah, so it is a very small sample size. It's definitely a big part of it. Yep, I think we would expect that this is not a normal distribution because everyone is also starting from a different place completely. And then there's one other main point as to why we would use a Wilcoxon signed rank test here. I would think about the study question. So in this case, the specific study question is trying to ascertain or understand, is the back pain, the distribution, was the back pain scores at the beginning higher or lower than what they were after 4 weeks? So really trying to answer the question, like, as a whole, is the set of data at baseline higher or lower than the set of data at 4 weeks? So those three things together, the sample size, the normal distribution or not, and then the question we're asking about, is there a distribution greater or lower from baseline to 4 weeks? Those are the three things that kind of point towards, like, okay, we should use a Wilcoxon sign rank test. Okay, so just like showing you some actual screenshots from, how you would go into SPSS and do it. And this kind of goes, this applies to any statistical test that you will do. I'm just going through the non-parametric test right now, but if you have, say you have your data, then you go to analyze, you go to non-parametric tests, then you go, in this case, there's again, we have so many different types of tests, so it's not gonna resonate right now. I think I still don't even know all of them. But you go to non-parametric tests, you go to legacy dialogues, two related samples. In this case, the samples are related, right? Because we have the same patients at baseline, measuring them again at 4 weeks. So that's not independent samples, it's the same group of people. So that's why we click two related samples. Then say my data is separated into pain score pre, which is pain score before acupuncture, and pain scores post acupuncture. And then I just select in here Wilcoxon, and I make sure I drag. So at the beginning, you'll see your data just looks like this, and we have to make sure we drag it into the variable columns. Select Wilcoxon. Those two other things down there are also other types of tests, but you select Wilcoxon and then you press OK. Oops. And then you're going to get 3 tables from SPSS that will help you interpret your results. So I'm going to go through those really quickly. So the output in SPSS is gonna give you 3 tables. And so the first table is descriptive statistics table, and we've already talked about descriptive statistics. And so that's where you're gonna get your sample size, your mean, standard deviation, range, and quartile statistics. So that's where you can use this table to just describe your samples. And that's kind of the lecture you probably got last time. And now the other 2 tables, the second table you'll get is called the ranks table. So this helps you kind of see how you kind of can compare your pre and post score. So you can see here, it might be a little difficult to read, but from the legend here, but if you see the little, I don't know what you call that, the exponent A, what that's doing is telling you that that 11 participants had higher pre-acupuncture treatment pain score than afterwards. So that's why there's 11 negative ranks. And then 4, so negative rank means that the pain score after is less than the pain score pre. So that's what we would want to see. So negative rank is good in this case. And then 4 participants had a higher pain score after the treatment or after the acupuncture. And then 10 participants had a tie. So they saw no change. Okay, so that's the ranks table. And then the last table you'll get is the test statistics. And we've obviously been talking a lot about test statistics overall in the last few minutes, but and that helps us. So now we've described the data. Now we've been able to summarize like how many patients actually saw an improvement or not. These are all still going towards kind of describing the sample. And then it's the test statistics table that really helps us make an understanding or a conclusion around, did this change that you saw from the treatment, is it actually statistically significant? Is it meaningful? And so like the output that Ayah showed you from the chi-squared test, we're looking at the async sig, that bottom there, that 0.07 number, that is your p-value. So if you get a p-value for 0.071, how would you interpret this result? And I don't want you guys to just say statistically significant or non-statistically significant. Tell me like how you would, what does this mean for your actual experiment? So if you had to write it up in a paper, what would this mean? Like, what would the conclusion be that you drew about these two groups of pre-treatment and post-treatment? Great. Exactly. So we would be able to conclude from this test that there is not enough evidence. There isn't that the results are not significant enough between to suggest exactly hala. Sorry, how do I say that? Hala, yeah. There is no statistically significant difference between pain scores pre and post treatment. So you could conclude as a physician from this study, obviously it's a very small sample size, so that has another set of problems, but we would want to say that, okay, the acupuncture did not really make a difference. Okay. Hopefully that example was helpful. So really, another quick review. When would you want to use a non-parametric test over a parametric test? So generally our default in statistics is to try to go through for parametric tests where we can, but when would we need to be using a non-parametric test? Awesome. Yeah, these are perfect. So exactly right. So when you have, most importantly, when your population is not following a normal distribution or is very skewed and you have outliers that you can't get rid of, when you have a very small sample size, and then when you have ordinal or ranked variables, etc. Awesome. Okay, so we just went through a Wilcoxon signed rank test. Can someone give me what would we call the null hypothesis for a test like this? Keeping in mind what the question for a Wilcoxon signed rank test is asking. Yeah, exactly, Ibrahim. So what we're really testing for this type of a test is are the distributions equal, or is one kind of greater than the other? Okay, and I'm gonna ask you, I put this question again to test you again. I know I asked it already, but want to review again. What does the Z-score allow you to do? This is like 10 slides ago. Awesome. Perfect, yes. So the Z-score allows you to understand how many standard deviations we are away from the mean, and it allows you to convert that distance from the mean in units that you can use to compare between groups. Okay, so that's, before we jump to questions and anything else, we did want to just thank you all for listening for this long. We've also put some really helpful websites that, I mean, at least for me, these were extremely helpful when I was in grad school and like trying to go through my own studies. And it was very difficult for me to keep track of all of these tests. And so the MGH Biostatistics Center has some really great resources on, you know, types of tests as well as code and definitions. And then this other link that we put here from UCLA shows you how to do all of these types of tests and analyses in different statistical packages. So if you're using SPSS, it takes you step by step, kind of like what I just did with the Wilcoxon example. And if you're using another package, it also has them in R and Stata and even Python if you were doing that, but I don't know why you would do that. So yeah, so hopefully these are helpful. And yeah, would love to use the remaining time. If you have questions for either of us, we can do our best to answer them.
Okay, thank you so much, Ayah and Zahra. So I'll try to read the questions. So Asma, is every statistical test has its particular p-value?
So I would say yes. So generally, you're always going to be, for the most part, comparing it to the significance level of 0.05 or 0.01. But the p-value that you get from each individual test that you run will be different depending on the association. I think that's what you're asking us, Matt, but we're happy to clarify more. Thank you.
I will also clarify that we are not doctors.
Not doctors. Not.
You are the doctors.
You are the doctors. But thank you so much, Muad.
So, and I would like to add, so when you report your results, most statisticians and most guidelines recommend that you report p-value in addition to confidence interval.
Yes.
Because this is very important, because as Zahra and Ayah mentioned, the confidence interval gives you kind of the confidence in your estimation or in the results. It's not only just a single value. And also I would like to add, and maybe Zahra mentioned that very briefly, now most statisticians, and that was like, there was a published report by the American Statistical Association, recommend not to use the word, the term statistical significance, but we used it here just to kind of make things easier. But when, you might hear that from like some, professors or some statisticians. So the alternative would be to say, for example, if you are comparing Gaza and West Bank, and you compare, for example, age, and you found that people in Gaza are younger. So you say, on average, the sample from Gaza, like their age was like less than, or the population were younger than the people from West Bank, without saying statistical significant or not. Or you can say there is an evidence that the population in Gaza are younger than West Bank. This is just a very minor point, but you might hear that in the future. Asma, how to choose which statistical test to run on my data? And I think Ayah and Zahra mentioned that, but could you please just repeat the kind of the flow chart or whatever, like the mind map?
Yeah, so this is a bit difficult to see, but there are so many different types of tests, but you start by what type of data do you have? So are you looking at continuous data in which you'll be examining the means? Is it normally distributed? Or do you look at the right side of the flowchart, in this case, binomial or multinomial, in which you'll be looking at proportions as opposed to means. So you see what kind of data that you want to investigate, and then you also have to consider how many samples. So, and for example, on the left side, how many samples, and then the next question you would ask, so say you have one sample, then you would go to where it says known population variance. Do you know the population variance, or is it unknown? And that allows you to determine which kind of tests that you run. So we mostly shared like the very brief basic tests, but the main types of questions you'll be asking yourself is, what type of data do you have? And how many groups do you have? And those kinds of questions. But once you start to learn some of the more advanced tests, you'll be able to determine like which is most appropriate for your type of study and your sample size that you have. But yeah, so I think that the tests that we mentioned, so we could give an entire lecture on ANOVA, for example, or an entire lecture on chi-square test. But it was just all very brief, and as you can see, so if you all are interested, and if it is something that OxPal would be open to doing in the future, we could do like a part 2 biostatistics lecture and expand on these concepts more. But that's something that we'll talk about, and we'll be in touch with you all and with Al-Khateeb and with OxPal. So yeah, this is just 4 of many different types of tests that you can look at.
Okay, thank you. I think there is a question about if the p-value is 0.05.
Yeah, I love this question. This is exactly what Usaid kind of, and we alluded to a little bit briefly, and this is kind of, again, one of the issues with statistical significance as a concept, and even the p-value as a concept. But if you're getting something of 0.05, then technically it's still registered as not significant. But then really it begs you the question, like, okay, what if you got 0.05, 0.049? Is it really that different? Basically, I can't answer that without, opening up a whole Pandora's box. But this is exactly the whole point of why there's some issues with this as a threshold to begin with.
Yeah, so it's important to report the confidence intervals and oftentimes run multiple tests.
Yeah.
Exactly, and I would second that because I had the exact same question. I asked it to one of my professors, so exactly, we are not looking only at exact p-value. We should also look at the confidence interval, and then see if the confidence interval is very wide and the p-value is 0.05. Then it's most likely that there's no difference. That's the most likely interpretation. So you shouldn't look only at the p-value. You should also look at the confidence interval.
Exactly.
So Brahim would recommend that we have part 2, and actually we discussed that with Ayah and Zahra. So hopefully, maybe in the summertime, after we end the research fellowship, maybe we'll have part 2. So if you have any kind of feedback, please recommend any courses, any specific test, any specific session in the feedback, and we are happy to look at the feedback and provide any session. Muad, and actually Muad is my brother. It depends on this. It depends on the size of effect we care about and how accurate we want to be. And I think he's referring to the p-value and whether it's 0.05 is significant or not. So we should look and have a more holistic approach rather than focusing on the exact p-value. For more than one statistical test be applicable to, can more than one statistical test be applicable to my data?
I would say yes, definitely. So if you are running a large research study, you will probably be running several different kinds of tests.
Okay, so just a follow-up to what we have discussed. I would just want to give a quick example. I want to hear from you just to kind of summarize the whole lecture. So if we have 2 groups, we are comparing Gaza and West Bank, and we are assuming, or even we run we do the histogram and we looked at the data and we found the data is normally distributed. Or actually the data are normal. It's because data is plural, and I realized that very recently. Anyway, so if we want to compare age and the data are normally distributed, would we use t-test, chi-square, ANOVA? I just want to give the most commonly used test.
Are you asking for our response to the slides or from the...
For the students, sorry. For the students and the doctors who have joined us. So if you want to compare age between Gaza and West Bank, would you use t-test, chi-square, or ANOVA? Okay. Ala says t-test. Yeah, age is exactly. So it's in continuous variable. It's not categorical variable. Any more responses? Yes, exactly. We are comparing the mean difference. Okay, that's fine. I think the answer is correct. So we are using t-test to compare age between the 2 groups. Just one more example before we end the lecture. So if we want to compare age and we categorize age, so we have, for example, from 10 to 20, 20 to 30, etc. And we want to compare the age as a categorical variable. What test should we use? Should we use t-test, chi-square, or ANOVA? Muad, yes. And Ala. Exactly. So we use chi-square because we are comparing categorical variable. And just to translate into Arabic, so when we use, like when we look at the test, we look at in Arabic المقارن فيه. So المقارن والمقارن فيه. So groups هي المقارن. So we compare Gaza with West Bank. المقارن فيه, or we compare in terms of what? We and then look at these variables, if they are categorical, if they are continuous, or if they are like normal distributed, not normal distributed. These are the things that determine the test. We don't look at the groups because we already have Gaza and West Bank. We look at the things that we want to compare Gaza with West Bank. For example, we look at age, look at gender, we look at other variables, and then look whether they are normally distributed or not normally distributed, and look at whether they are categorical or continuous. And I hope that makes things clear to all of you. And I'm not sure, Ayah or Zahra, do you have any questions or any comments?
To finalize the lecture, or about specifically what you said?
Whatever you want.
Okay. Yeah, I think you did a great job of summarizing everything. And I think Zahra and I are both more than available if you want to share our emails again. Yes. To stay in touch. Yeah, we're just very happy to get this lecture. So for us, connecting with people in Palestine is really important. I'm originally Palestinian. Zahra does a lot of work in Palestine. So just sharing knowledge and being able to use technology, connect with people in Gaza and West Bank is very, very rewarding for us. And we're just really excited and really, really just honored and happy to have these conversations with you all. And we're excited for you all to conduct amazing research studies and get excited about biostatistics and how you can apply it to your research and the issues and the topics that you all care about. So yeah, just thank you. That's all I have to say.
Thank you. Zahra, do you have any comments, any things before we end the lecture?
No, I think you guys said it well. Actually, I don't know if people saw Muad's question, his last question. I think it's a really good one that will help actually tie the lecture together. But, you know, biostatistics is full of ways to try to quantify how meaningful your results are, right? We're trying to do that. And all of these statistics, p-values, confidence intervals, these are all attempts to quantify meaning. But he asked a really good question, which is statistical significance the same as clinical significance? And, you know, I'm not a physician, but this is actually a very important question where actually your judgment as the physician or as the doctor is going to come in. So in a certain experiment or a certain test that you're running, even if something spits out as what we call statistically significant, that doesn't mean it necessarily translates into something that's going to be valuable for the patient or that is important for the patient in your scientific expertise. So just keep that in mind also. The field of statistics is really an attempt to quantify the world around us, but ultimately you're going to be using your clinical judgment to know, like, okay, if you see this change, just because the paper said it's statistically significant doesn't mean if in real life you're observing all the time, or if you know that a certain trend is happening with your patients that you've been putting in practice, you have to consider both of those at the same time. So to also put a word of caution on, like, it's easy to get very overwhelmed with a lot of numbers and a lot of tests, but ultimately that needs to go hand in hand with whatever your clinical expertise is and what that's actually translating to in real life.
Thank you so much, Zahra. And just a final comment, I would always kind of recommend having a mentor or supervisor who is a clinician scientist if you are conducting a clinical study. Because as Zahra mentioned, you need the clinical experience to judge whether something is clinically important or not. And that's why, like, I don't recommend anybody, especially like when you are a medical student or a newly graduate from the medical school, to do a study on your own without asking more kind of senior physicians who have at the same time research experience. So thank you so much, everyone, for joining us, and thank you, Ayah and Zahra, for the wonderful lecture. We'll upload the lecture on our YouTube channel, and hopefully we'll see you in the last two lectures, and they will be about academic writing. Thank you so much. Take care.
Thank you all.
Thank you.
Assalamu alaikum. Ma as-salama.
Bye.